This lecture will cover some examples of integration by trigonometric substitution. So as the name implies, you're trying to integrate and you're using trig expressions as substitutions. So what will happen is we'll have some integrand which we can't solve using some other form like a u substitution or integration by parts, and it has perhaps some Pythagorean form to it, such as a Pythagorean difference in this case or a Pythagorean sum in other cases, and we will try to find substitutions. So in this case, 25 minus x squared, this is something squared minus something else squared. Well, we can imagine that this would allow us to put a hypotenuse of 5 up here. Our legs then would be rad 25 minus x squared and x. Now theoretically these could be switched compared to this angle theta, but generally we'll put just the simple variable here on the opposite if we have the choice. So now we're trying to find expressions for the different things in our integrand in terms of theta. So we have to find something for the denominator and something for the dx. So first, dealing with the denominator, we know that the cosine of theta is adjacent over hypotenuse, and we don't choose to use these two. We want to minimize the number of variables if possible, so we always try to use the 5 when we can. This leads to rad 25 minus x squared is 5 cosine theta. Meanwhile, to get dx, first we need x. So sine theta is opposite over hypotenuse, so that'd be x over 5. And we try to relate to the number rather than relating the two variable pieces together. So x is 5 sine theta, therefore dx is 5 cosine theta d theta. So now we have an expression for the cube root of the denominator because of this 3. We have an expression for dx, the numerator, and we plug these things in. So the denominator is going to be this expression cubed, so 5 cubed times cosine cubed theta. Numerator is 5 cosine theta d theta. We cancel some things, so the extra 5's come out as a 1/25. Cosine over cosine cubed is 1 over cosine squared, which is the same as secant squared. I can integrate secant squared into tangent, so it's 1/25 tan theta plus c. And of course, because I began with x's, I should finish with them. Now I go back to my triangle. Tan theta is opposite over adjacent, so that's x over rad 25 minus x squared. And so this is my final answer. Okay, similar example. We even have a similar setup of our triangle where this again is something we can't integrate in some other more elementary fashion. If we had just say an x up here, we would make u 25 minus x squared because our du would go with our x dx up here, but we don't have that situation. So we know this would be a leg with the hypotenuse then being 5, because when you square it you get 25, and therefore our other leg is x. We need to substitute in for these two pieces. So sine theta is opposite over hypotenuse, so x over 5, which again leads to our dx is 5 cosine theta d theta. Meanwhile, we have to find an expression for rad 25 minus x squared, so we know that cosine theta is adjacent over hypotenuse. So therefore, rad 25 minus x squared is 5 cosine theta. Plugging these two expressions into our integrand, we get this one. A lot of stuff cancels. We get just d theta. Integral of d theta is, of course, theta plus c. We go back to our triangle. There's different ways of expressing theta, but we want to use simpler expressions if possible. So we eschew the rad 25 minus x squared in favor of using this leg x and the hypotenuse. So this is an opposite, this is an hypotenuse. So we know the sine theta is x over 5 as we saw up here. So therefore, theta is the inverse sine of x over 5. So you actually may recognize this result somewhat from earlier sections way back when we talked about formulas involving integrating to inverse trig. You could have done this much more directly. Now we're starting to get a little more complicated. Integral of rad 4x squared plus 9 over x to the 4th dx. Well, now we have a Pythagorean sum here, not a Pythagorean difference, and so this is going to represent our hypotenuse. So that's our hypotenuse, where we have legs of the square root of each of these pieces. So one leg is 2x, and the other leg should be 3. And so we need to find ways to substitute in. So we know that secant theta is hypotenuse over adjacent. I could use cosine, but we're trying to keep this in the numerator. So secant theta is hypotenuse over adjacent, and so therefore you multiply 3 to both sides. So now I have an expression for the numerator. The numerator is 3 secant theta. I've got to still deal with the x to the 4th and the dx. Well, tan theta I know is 2x over 3. So now I can solve that for x. X is 3/2 tan theta, which gets me my denominator. To get a dx, I differentiate both sides. So dx is 3/2 secant squared theta d theta. So now I can plug in the 3/2 secant squared theta d theta. I'm going to have to take this piece to the 4th power, and also I plug in here. So a lot of stuff to put in. So there's first of all the 3 secant theta. Then the denominator, I've got to take 3/2 tan theta to the 4th power, and then finally my dx is 3/2 secant squared theta d theta. Lots of simplifications here. I have 8/9 on the outside from all of these different constants coming together. 1 over cosine cubed, cosine of the 4th over sine of the 4th. I just expressed everything in sines and cosines, and then we can go back and simplify that, and we get all the way down to here. So I've gone from x's to thetas, but now I got to go even farther. I need to do a u substitution. So I went from x to theta now to u. I'm going to make u sine theta, so therefore my du is cosine theta d theta. The 8/9 doesn't do anything for me right now. I have a u to the 4th in the bottom and a du on top, so that's u to the negative 4 du. So now I can just use power rule, add 1 to the exponent and divide by it, so it's u to the negative 3 over negative 3 plus c, because I finally integrated. So I went from x to theta to u, now I got to go from u back to theta back to x. Okay, so first thing I do is rewrite this a little bit to put the negative 3 over here with the 9. Now, u to the negative 3, okay, well, u is sine theta, so u to the negative 3, reciprocal of sine is cosecant, so that's how I get the cosecant cubed. Cosecant is hypotenuse over opposite, so cosecant will be rad 4x squared plus 9 over 2x. So now I got to get back to x's, so I plug rad 4x squared plus 9 over 2x in for cosecant, and then try to do a little bit more simplifications, and you finally get down to your answer. Couple more examples. Okay, a lot going on here as well. This one, almost like a Pythagorean sum, but you need to complete the square. So to complete the square, where half of 4 is 2, you square it and you get a 4, so we split this piece up. So now we've completed the square. We see we have a Pythagorean sum on the bottom, and so that's going to be our hypotenuse, which means we have one leg which is x plus 2, another leg which is 2. We need expressions for x, then to get differentiate to get dx, and also for our denominator. So to get the denominator, notice that secant theta is just hypotenuse over adjacent. And so here it is. I just multiply 2 to the other side, and now I've got my denominator is 2 secant theta. To get an expression for x, we use these two legs. So tan theta is x plus 2 over 2. Multiply by 2 and subtract 2. And so that's x, and I've got to differentiate to get dx. I take all of those expressions, plug them into my my integral, and I have all of this. So this was my x, 2 tan theta minus 2. My denominator was just 2 secant theta, and my dx was 2 secant squared theta d theta. Let's get some 2's on the outside. A few things these 2's cancel. I factored out a 2. Then what I can do is distribute secant theta to get a couple different integrals. So secant theta tan theta minus secant theta. The integral of secant theta tan theta is secant theta. Integral of secant theta is ln secant plus tangent. I distributed the 2. So now I got to get back to x's. Secant theta is hypotenuse over adjacent. So here it is. Here's my secant theta. And then tangent theta is opposite over adjacent. So this would be a perfectly acceptable answer, but you can do a little bit more, and so we do. First of all, I can cancel these 2's out. Another thing you can do is realizing that you could factor out a 1/2 here, and then you'd have a natural log of a quotient, which becomes the log of differences. Basically what I do is, rather than having these two denominators, I subtract 2 ln 2. And finally, 2 ln 2 is some random constant, c is some random constant, so I just combine them into some new random constant, which I called c star. So any one of these 3 answers is fine, but getting it all the way down to here is something you might see in the solutions, and you should be aware of what took place. So again, these I factored out from these 2 fractions, which allowed me to have a log of a quotient, which then I made into the difference of 2 logs, and I took the constant one and put it into my c. And finally, when written out, we have the integral of e to the x rad 1 minus e to the 2x. a little difficult to tell that this involves trig substitution, but if you think of this as 1 squared minus e to the x squared, then we have square root of 1, or 1 is our hypotenuse, a leg is e to the x, and another leg is rad 1 minus e to the 2x. So I know that e to the x will be secant theta because that's e to the x, because that's hypotenuse over, let's see, adjacent over hypotenuse is, oh, this should be cosine theta. Okay, I aborted the last one just to show you actually one more example that doesn't involve integration by parts, to simplify things down a little bit, just to make sure that you understand that not everything's going to go with integration by parts. This situation, it looks like you have a Pythagorean difference. You do, and so naturally you might think, well, I have to do integration by parts, whereas you can do a simple u substitution because this is a one higher power than over here. If we make u 16 minus 4x squared, our du is negative 8x dx. So I'd have a negative 8 on the inside, which means a negative 1/8 on the outside. So this part here goes into my du. This part is e to the 1/2. Notice my limits of integration have changed, because if I do 16 minus 4 times 2 squared, I get 0, and 16 minus 4 times 0 squared, I get 16. I remove the negative and flip my limits of integration, use the power rule, and simply plug in the upper limit, subtract the lower limit. So make sure that you're always keeping your mind open to all different possibilities of how to integrate these.